Hello and welcome to another video. This is a recitation video for the topic of second law of thermodynamics. So let's start with the first problem. We have a 600 megawatts power plant with a thermal efficiency of 40%. We are cooling this power plant by rejecting heat into a nearby river. We are asked to find the amount of rejected heat. What do we know? We know that thermal efficiency is 40%, right? Now, by definition, thermal efficiency is power output, right, over the heat input. From the first law analysis of a heat engine, and we know that a power plant is a type of heat engine, we know that QH is equal to the amount of work plus the amount of heat rejected, right? So thermal efficiency is W dot over W dot plus Q dot L. Now we know that W dot, the problem says, is 600 megawatts. So 600 megawatts over 600 plus Q dot L, which is the amount of heat rejected to the river, is equal to 40% or 0.4. Do the calculations and you get Q dot L is equal to 900 megawatts. So 900 megawatts worth of energy is rejected to nearby river. So the only part of this problem that you needed to use previous information is that the first law analysis states that W dot is equal to Q dot H minus Q dot L. So if this is our heat engine, this is the heat source, and this is the heat sink. This will be QH. This will be QL. And this will be W net or W net. Okay, so knowing these, we can use the definition of thermal efficiency, plug in some numbers, and find the final answer. Okay, problem 2. Basically the same thing. We have a power plant. This time it's 150 megawatts power plant. We get the consumption rate in the form of 60 tons per hour of fuel. The chemical energy released by the fuel is also given, 30,000 kilojoules per kilogram. We are asked to find the overall efficiency of the plant. W dot is 150 megawatts. Okay, how about QH? Q dot H is the amount of energy provided to our heat engine, in this case, our power plant. Our power plant is burning 60 tons of fuel per hour, and every kilogram of that fuel is giving us 30,000 kilojoules. So overall, Q dot H is 60 tons, which is 60 times to the power of 3 kilograms per hour. Well, obviously we want to change that to seconds, so times 1 hour over 3,600 seconds times the rate of release of chemical energy, which is 30,000 kilojoules per kilogram. Now here, 1 hour cancels 1 hour, kilogram cancels kilogram, and we end up with 5 times 10 to 5 kilowatts, or 500 megawatts. Now we know that by definition, the thermal efficiency of a power plant or a heat engine is W dot over Q dot H, right? So 150 megawatts over 500 megawatts gives you 0.3. So the efficiency of this power plant is 30%. Okay, we have an air conditioning unit which is cooling down a house at a rate of 750 kilojoules per minute, and it's consuming 6 kilowatts of electric power. We are asked to find the coefficient of performance and the rate of heat transfer to the outside air. So for a problem like this is the house, right? This is our AC unit. It is consuming 6 kilowatts of power. It's absorbing 750 kilojoules per minute from the house, and it's dumping Q dot H, which is unknown, into the outside air, right? So this is a schematic of our problem. Now, first of all, this is an AC unit, and you know that AC unit grabs the heat or absorbs the heat from the low temperature sink. So this guy over here is actually our Q dot L. Okay, so let's first make the unit into something useful. So Q dot L is 750 kilojoules per minute. I want to change that to per seconds, so I'm gonna multiply this by 1 minute over 60 seconds, which gives us 12.5 kilowatts. Okay, now this is a unit that I'm comfortable working with. Let's go to part A. COP of a refrigerator, which AC unit is a refrigerator cycle. So COP of a refrigerator cycle is Q dot L over W dot. So it's 12.5 over the W dot, 6 kilowatts, which gives us 2.084. So this is the coefficient of performance of this AC unit. Now for part B, we are interested in Q dot H, which is the rate of heat transfer to the outside air. So first law analysis says that Q dot H minus Q dot L is equal to W dot net. So Q dot H is W dot, 6 kilowatts, plus Q dot L, 12.5, which gives us Q dot H is 18.5 kilowatts. Okay, problem 4. We have a heat pump, which is basically a refrigeration cycle, but the goal is different. Instead of keeping a space cool, we want to keep a space warm. So a heat pump is keeping our house at a constant 23-degree temperature. Now this house is losing 60,000 kilojoules per hour of heat through the walls, through the cracks in the windows, and such. The people inside and the electronic devices in the house are generating 4,000 kilojoules per hour worth of heat. If this coefficient of performance of this heat pump is 2.5, we are asked to determine the required power input of this heat pump. Again, this is our house. We have the heat pump here. We want to keep this house at a constant temperature. So we are providing Q dot H. We are receiving the heat or absorbing the heat from the cold outside in the form of Q dot L, and we are consuming some power. We're asked to find this power input. So the house is losing 60,000 kilojoules per hour, while also generating 4,000 kilojoules per hour worth of power. Okay, now in order to keep the temperature inside constant, meaning in order to keep the internal energy of the fluid inside at a constant level, we need to provide whatever energy is lost using the heat pump. So Q dot H, which is the heat pumped inside the house, is equal to the amount of heat the building is losing minus the amount of heat that the building is generating through the people inside and the electronic devices. So that will be 60,000 kilojoules per hour minus 4,000 kilojoules per hour, which will give us 56,000 kilojoules per hour. Now, kilojoules per hour is not a very useful unit, so Q dot H is 56,000 kilojoules per hour times 1 hour over 3,600 seconds, which will give us 15.56 kilowatts. So the heat pump is producing 15.56 kilowatts worth of power. COP of a heat pump is Q dot H over W. So that is 2.5 is 15.56 over W dot. Doing the math, we get that the W dot, or the power input, is 6.23 kilowatts. So the key to these problems is that they are usually worded in a way that they don't directly give you the amount of Q dot H that the heat pump needs to produce, but they give you the amount of heat that the building is losing, or if there are electronic devices inside, if they have significant effect, the amount of heat that they are generating. They would do this wording for air conditioning and refrigerator problems as well. They don't directly give you the number. They try to manipulate the wording of the problem. But if you think about it, it's rather easy. The building is losing 60,000 kilojoules per hour worth of power, so the heat pump has to support that number in order to keep the temperature constant. That's the only trick to these kind of problems. Okay, problem 5. Now we are talking about a residential heat pump again. This time the refrigerant or the working fluid inside the cycle is given. It's R134A. It enters the condenser at 800 kilopascals and 40 degrees Celsius. The mass flow rate is also given. It leaves the condenser with the same pressure, this time as a saturated liquid. Now, if the compressor power input is 1.2 kilowatts, we are asked to find the COP and the rate of heat absorption from the outside air. Let me give you a brief drawing of the cycle that we're dealing with. So this is the evaporator. The working fluid then enters the compressor. After the compressor, it goes into the condenser. And then it goes through a throttling valve and goes back to the evaporator. And this is the direction of the cycle. Okay, so what we know is we know the state of our fluid here, point 1, when it enters a condenser at 800 kilopascals and 40 degrees Celsius. Then we know the state at the exit here, where we know that it has the same pressure, 800 kilopascals, and this time it's saturated liquid. We are asked to find the COP. Now for part A, COP of a heat pump is Q dot H over W dot. Now, on this cycle, where is Q dot H? Heat pump rejects the Q dot H into the area that we want to keep warm. The working fluid loses its energy in the condenser. So Q dot H actually happens here. This is where the fluid cools down and rejects the heat into the house or whatever. So let's do the first law analysis on the condenser. Now, if we do that, so first law analysis on the condenser, what we get is that Q dot H is equal to the m dot of the fluid, H1 minus H2. This is a single stream control volume. We only have one entrance and one exit. We don't have any works involved. So whatever heat this condenser is losing is equal to the change of enthalpy of the fluid entering and exiting, neglecting kinetic and potential energies. So in order to find H1 and H2, we need to check the tables. So let's check the tables at state 1. We get that at state 1, we are dealing with a superheated vapor, because 40 degrees Celsius is greater than the saturation temperature of R134A at 800 kilopascals. So from the tables, we get that H1 is 276.45 kilojoules per kilogram. Now, how about H2? H2, the problem specific states that at state 2, we are dealing with a saturated liquid. So H2 is equal to H of F at 800 kilopascals, which is, from the tables, 95.47 kilojoules per kilogram. Okay, now we can plug everything back here and get Q dot H is m dot, which is given 0.018 times 276.45 minus 95.47. You do the math, you get that Q dot H is 3.257 kilowatts. Now I can find COP. COP of this heat pump is 3.257 over 1.2. It is 2.71. Now for part B, we are looking for the heat absorption from the outside air. That is Q dot L here, happening on the evaporator. So from the first law analysis, we know that for a cycle, Q dot H minus Q dot L is equal to the W dot. Playing with this equation, we get that the Q dot L is Q dot H minus W dot. You can plug in some numbers and get that Q dot L is 3.257 minus W dot, which is 1.2. Q dot L is 2.057 kilowatts. Okay, problem 6. We have a Carnot heat engine that is operating between a heat source of 1000 Kelvin and a heat sink at 300 Kelvin. Now, if this heat engine is consuming 800 kilojoules per minute, that E shouldn't be there, it's not mine, it's min, determine the thermal efficiency and the power output of the engine. First, this shouldn't be here. Now, a Carnot heat engine is a reversible heat engine, which means it's ideal. So we can calculate the thermal efficiency of this cycle using the reversible ideal thermal efficiency function, which is 1 minus TL over TH. Now, TL is the temperature of the sink, TH is the temperature of the source. With that in mind, thermal efficiency is 1 minus, keep in mind that the temperatures in this equation need to be in Kelvin, so that would be 300 over 1000, which is 0.7. Now, in order to answer part A, our thermal efficiency is 70%. Now, for part B, we are asked to find the power output of the engine. Now, we know efficiency is W dot out over Q dot H, right? For a heat engine. Now, we know how much this heat engine is consuming here, 800 kilojoules per minute. That is QH. How do we know it's QH? It is the amount of energy that the heat engine is consuming. Q dot H is the amount of energy that the heat engine receives or consumes. Okay? So that's how we know that Q dot H is 800 kilojoules per minute. Now, again, 800 kilojoules per minute is not a unit that I'm comfortable with. So, Q dot H is 800 kilojoules per minute. I'm gonna multiply this by 1 minute over 60 seconds, right? So minutes cancel each other, and I get Q dot H is 13.34 kilowatts. Okay. Now this is a familiar unit. I can plug this back into our equation and find the W dot. So from part A, I know that thermal efficiency is 0.7. W dot is unknown. Q dot H is 13.34. Do the math, and you get W dot is 9.33 kilowatts. So the only thing about this problem is that we used two different definitions for thermal efficiency. This is the traditional one, and this is for the Carnot cycle one. Now, because the problem specifically says that we are dealing with a Carnot heat engine, we can use this and then use the info from here and plug it into this. All right, problem 7. We are dealing with a refrigerator now. This refrigerator is removing 300 kilojoules per minute of heat from a cooled space. The temperature of this cooled space is minus 8 degrees Celsius. Now, the kitchen temperature, the kitchen air temperature is 25 degrees. Refrigerator dumps or rejects the heat into the kitchen. Determine the minimum power required for this refrigerator. Now, when we are asked to find the minimum power required to operate a refrigerator or a heat pump, or the maximum power output of a heat engine, it's a clue that we are dealing with a reversible ideal cycle. So let me draw a schematic of this problem first. So this is our refrigerator. This is our cool space. And this is the kitchen. It is taking heat from the cool space at the rate of 300 kilojoules per minute, and it is dumping it into the kitchen. Temperature of the kitchen is 25 degrees Celsius. Temperature of the cool space is minus 8 degrees Celsius. So COP of a refrigerator, which is acting on a Carnot cycle, or is ideal, is, we know this equation beforehand, it is 1 over TH over TL minus 1. Now, TH is the temperature of the kitchen, and TL is the temperature of the cool space in Kelvin. So this gives us 1 over TH in Kelvin is 25 plus 273. TL is minus 8 plus 273. Do the math, and we get that the coefficient of performance of this refrigerator, which is acting on a Carnot cycle, is 8.03. Now, the reason, again, that we are assuming that this fridge is on a Carnot cycle is because we want to find the minimum power required. COP of the refrigerator also is Q dot L over W dot. So I can say 8.03 is, problem says it is taking 300 kilojoules per minute. I'm going to put 300 here and then solve for W dot. Now, if you do that, you get that W dot is 37.36 kilojoules per minute. Now, kilojoules per minute is not a unit that we are usually dealing with. So I'm going to multiply this by 1 minute or 60 seconds. And I'll get W dot is 0.622 kilowatts. So basically, the key word in the problem was minimum power required. When you see that, you know that you need to assume that the cycle is operating on a Carnot cycle and then do the calculations. All right, problem 8. We have a heat pump that is keeping the temperature inside the house at 22 degrees. Now, this house is losing heat at a rate of 110,000 kilojoules per hour. This pump is consuming 5 kilowatts of power to absorb heat from the outside air, which is at 2 degrees Celsius. Now, the question is this pump strong enough to do this job? Now, when you are dealing with problems that ask you whether or not a cycle is feasible, a cycle is strong enough, or something like this, you have to compare this cycle to a reversible ideal or a Carnot cycle acting between the same two heat sources, and then compare your results with the results of an ideal cycle, and then draw a conclusion. Okay? So here we have an actual cycle that is consuming 5 kilowatts of power. We are going to see how much power does an ideal reversible cycle consume and compare the two to see if this one is strong enough. So let's start. First, let's make this kilojoule per hour unit something more useful. So the amount of heat that the house is losing, we did this a few problems back, is equal to the amount of heat that the heat pump is pumping into the house. Q dot H is 100,000 kilojoules per hour times 1 hour or 3,600 seconds. Do the math, you get that Q dot H is 30.56 kilowatts. Okay. Coefficient of performance of a heat pump operating on a Carnot cycle is COP of the heat pump, Carnot, is 1 over 1 minus TL over TH. Again, TL is the temperature of the heat sink, and TH is the temperature of the heat source, both in Kelvin. So 1 over 1 minus, now TL is 2 degrees Celsius. In Kelvin, that is 275. 22 in Kelvin is 295. You do the math, you get 14.25. Now again, we know that the same coefficient of performance is Q dot H over W dot, right? So 14.25 is equal to Q dot, we already know, is 30.56. W dot, which is the minimum. The reason we can add subscript of minimum to this W dot is that we are dealing with a Carnot heat pump. So the W dot minimum is 2.072 kilowatts. Now our actual heat pump is consuming 5 kilowatts, which is more than the minimum power of 2.072. So this heat pump is strong enough. So basically, this problem asks us whether or not a system is feasible, a system is possible. The only way that you can answer that question is for you to compare your actual system, your actual heat pump, refrigerator, heat engine, whatever, with a reversible ideal one or with a Carnot one. We have equations to find the coefficient of performance or efficiency of a Carnot cycle. Use that to find the minimum or maximum power output and then do the comparison. For a heat pump and a refrigerator, which are power consuming devices, the actual power consumption has to be larger than the power consumed of a Carnot cycle. For a heat engine, which is a power producing device, the actual power produced has to be smaller than the power produced by a Carnot cycle. Problem 9. We are dealing with R134A again as our working fluid in a refrigerator. This refrigerator is keeping the cool space at minus 35 degrees Celsius. It is rejecting heat into a water stream that enters the condenser at 18 and leaves at 26. So it's just like a river. Instead of dumping into a river, we're dumping into a water stream. The mass flow rate of the water is given, and we know that this refrigerant enters the condenser at 1.2 megapascals on 50 degrees Celsius and leaves with the same pressure, this time subcooled by 5 degrees Celsius. Now, if the compressor is consuming 3.3 kilowatts of power, we are asked to find the mass flow rate of the refrigerant, the refrigeration load, the COP, and the minimum power input for the same refrigeration load. So, let's draw a schematic of our cycle. This is the evaporator. This is the compressor. Then we have the condenser. Then the throttling valve. And that's it. We are back to the evaporator. This is the direction the refrigerant is moving in the cycle. So inside the condenser, we have a water stream. This water enters and leaves like this. It enters at 18 degrees Celsius and exits at 26 degrees Celsius. So our refrigerant is absorbing Q dot L, or the refrigeration load, in the evaporator and then dumps it in the condenser to the water, while consuming 3.3 kilowatts worth of power. What else do we know? We know that it enters the condenser at state 1 at 1.2 megapascals of pressure, 50 degrees Celsius temperature. We know that it leaves the condenser at the same pressure, so 1.2 megapascals again. Now this time 5 degrees subcooled. So what does this mean? 5 degrees subcooled means it is 5 degrees Celsius below the saturation temperature of our refrigerant at 1.2 megapascals of pressure. We are asked to find the mass flow rate of our refrigerant. Now, this condenser here is a heat exchanger. We have two streams of two different fluids enter and exit this heat exchanger. So I'm going to write the first law analysis for a heat exchanger. So first law analysis. So for R134A, we have Q dot H is equal to mass flow rate, which is unknown, enthalpy 1 minus enthalpy 2. So the amount of heat that the refrigerant is losing is equal to the change of enthalpy between states 1 and 2. For the water, because water is inside the heat exchanger and it's absorbing all of the heat lost from the refrigerant stream, we get Q dot H is m dot of water times delta H of the water. Now, if you remember from our last recitation video, I'm going to put the link in the description down below. Delta H of a liquid is its specific heat times temperature difference. So m dot of the water stream times C of water times delta T. Now, inside the heat exchanger, there is only these two streams, and whatever heat one of them is losing is equal to the heat the other one is gaining. So m dot of the refrigerant, H1 minus H2 of the refrigerant, is equal to m dot of the water stream, C of the water, delta T of the water. Now I'm going to play with this equation. Okay, so let's start by finding the enthalpy of our refrigerant at states 1 and 2. So at state 1, it says the pressure is 1.2 megapascals and the temperature is 50 degrees Celsius. You can check the tables for the refrigerant R134A. I've put a link to a PDF format of the tables down in the description below. You will see that we are dealing with a superheated vapor. So we can just read the enthalpy from the table. It is 278.27 kilojoules per kilogram. Now, state 2, again, the pressure is 1.2 megapascals. Now we're 5 degrees subcooled. So the temperature at state 2 is the saturation temperature at 1.2 megapascals of pressure minus 5. That is 41.29 degrees Celsius if we check from the table. Now for a subcooled liquid, we can estimate the enthalpy using this equation. Enthalpy of the subcooled liquid is H of F at the temperature we have, 41 degrees, plus the specific volume of the liquid, saturated liquid, at 41 degrees Celsius times pressure of our fluid minus the saturation pressure at 41 degrees Celsius. Now from here, you just need to plug in numbers. H of F at 41 degrees Celsius is 109.75 plus V of F is 0.00087. P2 is 1200 kilopascals minus P of saturation is 1044.95. Do the calculations and we get H2 is 109.88 kilojoules per kilogram. So we got both H1 and H2. M dot of the water is given inside the problem here. This is m dot of the water. C of water is 4.2 kilojoules per kilogram Kelvin. You can read it from tables or you just can memorize it. Delta T in this equation is 26 minus 18, which is 8 degrees Celsius, right? We have everything. We can plug them all back into our equation here. Okay, just cleaned up the calculation area and dragged all the important information down here. So our unknown m dot times h1, 278.27, minus h2, 109.88, is equal to mass flow of water, 0.25, times C of water, 4.2, times the delta T, 8. Do the math, and we get that mass flow rate of our refrigerant is 0.05 kilograms per second. So what we did is that we focused on the condenser as a heat exchanger. We already knew the change of enthalpy of one of the fluids, the water stream, and then used that information to find the unknown mass flow rate of the refrigerant flow. Because the change of enthalpy of the water stream is equal to the amount of heat that the water stream absorbs. That heat is equal to the amount of heat that the refrigerant is rejecting or is losing in the condenser. We use that to find the missing mass flow rate. Now let's move to part B. So for part B, we are looking for the refrigeration load. Now refrigeration load is the amount of heat that the refrigerator needs to absorb from the cooled area. That is Q dot L. So the first law analysis of a cycle shows that Q dot H minus Q dot L is equal to W dot. Now using that, I would say Q dot H, I already know the number for it. It is 0.25 times 4.2 times 8. Remember, this is the change of enthalpy of the water stream. This is Q dot H minus our unknown Q dot L is equal to 3.3 kilowatts, which is a power input of the compressor. Now remember, this is Q dot H that we found from part A. Doing the math, you get Q dot L is 5.1 kilowatts. Now this was super easy. You just need to know that for a cycle, all the heat coming in minus all the heat going out is equal to the work. That's what we got here. Q dot H minus Q dot L is equal to W dot. Now Q dot H, we found it from part A. It is equal to the change of enthalpy of the water stream. So that's the equation. Q dot L is the unknown, and W dot, the problem says, is 3.3. Plug in numbers, we found 5.1 kilowatts worth of refrigeration load. Now let's move to part C. So part C asks for the coefficient of performance. Now coefficient of performance of a refrigerator is Q dot L over W dot, which from part B we know Q dot L is 5.1, W dot is 3.3, so COP of this refrigerator is 1.55. Now part D asks for, again, the minimum power input for the same refrigeration load. This is like the previous problems. We are asked to find the minimum power input for a power consuming cycle refrigerator. So we are going to treat it as a Carnot cycle. Coefficient of performance of a refrigerator which is operating on a Carnot cycle is 1 over TH over TL minus 1. Okay, now you may say, all right, the cold temperature is minus 35, but what is the hot temperature? We don't have any temperature for the condenser. We only know that the water stream enters at 18 and leaves at 26. In a scenario like this, you can say that the temperature of the hot area is the average of water inlet and outlet temperatures. So that will be 26 plus 18 over 2, which is 22 degrees Celsius. So the temperature of the hot reservoir in this problem is the average of the temperature of the water inlet and outlet, which is 22 degrees Celsius. Now we can plug them back into our COP equation. That gives you 1 over 295 over 237 minus 1, which is 4.08. Now I can say that COP of my Carnot cycle is also refrigeration load over the minimum amount of heat input. Plug in numbers, I get 4.08 is the problem specifically say it's the same refrigeration load, so 5.1 over the minimum power input. You do the math, you get that the minimum power input is 1.25 kilowatts. So if our refrigerator was operating on an ideal reversible cycle, it will consume only 1.25 kilowatts instead of the 3.3 kilowatts that it's actually consuming right now. Again, we were asked to find the minimum power input of a power consuming cycle. That is your clue to go for the Carnot coefficient of performance equation. Okay, problem 10, our final problem. We are dealing with an air conditioning unit with a working fluid R134A. It is keeping the room temperature at 26 degrees by rejecting heat the outdoors at 34 degrees Celsius. This room is gaining heat from the outside at a rate of 250 kilojoules per minute, and the people and the devices inside are generating an additional load of 900 watts. We know that the refrigerant enters the compressor at 500 kilopascals as a saturated vapor. The volumetric flow rate at the entrance is also given, 100 liters per minute, and then leaves at 1200 kilopascals and 50 degrees Celsius. We are asked to find the COP, maximum COP possible, and the minimum volumetric flow rate of this refrigerant and the compressor entrance for the same compressor inlet and exit conditions. So I'm just going to give you a schematic of this problem. We have the evaporator, we have the compressor, we have the condenser, and the throttling valve is the final component of the refrigeration cycle. These arrows show how the refrigerant rotates in this cycle. So what we know is that here at state 1, refrigerant is 500 kilopascals and saturated vapor. We also know that here at state 2, it is 1200 kilopascals and 50 degrees Celsius, right? The volumetric flow rate at 1 is also given. So volumetric flow rate at 1 is 100 liters per minute. So for part A, COP of a refrigerator is Q dot L over W dot, right? Now, what is Q dot L? Q dot L is the amount of heat that the AC unit is absorbing in the evaporator, right? So this is Q dot L. Now, the evaporator is actually the house that we are talking about. Now, this house is gaining heat at a rate of 250 kilojoules per minute from the outside, and it's also generating 900 watts from the people and everything inside. So Q dot L is equal to amount of heat that this room is gaining from outside plus 900 watts, because we have to reject this heat in order to keep the temperature constant. So Q dot L is 250 kilojoules per minute. I'm going to change the units, so times 1 minute over 60 seconds plus 900 watts or 0.9 kilowatts. So keep in mind that I did this in order to change the units to kilowatts. And if you do the math, you get that Q dot L is 5.07 kilowatts. Okay, I got Q dot L, but what about W dot? In order to find the work input of the compressor, we need to do a first law analysis of this compressor. It's a single stream steady state device. Refrigerant enters at 500 kilopascals and exits at 1200 kilopascals. So if we do a first law analysis for the compressor, we get that W dot is M dot H2 minus H1. The amount of work that the compressor consumes is equal to the rise of the enthalpy of the working fluid. So I need to find H2, H1, and M dot. Let's start with H1. So at state 1, we are dealing with 500 kilopascals pressure and saturated vapor. So H1 is H of G at 500 kilopascals. Check the tables, and you can see that H1 is 259.3 kilojoules per kilogram. At 2, we are talking about 1200 kilopascals and 50 degrees Celsius. Now this is superheated vapor. Check the tables for superheated R134A, and you will see that H2 is 278.27. Now, for the M dot, I only have the volumetric flow rate at the entrance. Now I know that M dot is volumetric flow rate over the specific volume at state 1. The specific volume at state 1, because we are dealing with a saturated vapor, is the specific volume of saturated vapor at 500 kilopascals. So let's read that from the table as well. That is 0.041118 meters cubed per kilogram. So the volumetric flow rate is given in the units of liters per minute. We need that to be in meters cubed per second. So let's get to that first. So volumetric flow rate 1 is 100 liters per minute. We need to first change the liters to meters cubed. So I'm gonna multiply that by 1 meters cubed over, conversion rate is 1,000 liters. And then we need to change the minutes to seconds. So times it by 1 minute over 60 seconds. Now if we do that, we get that the volumetric flow rate at 1 is 0.0017 meters cubed per second. Now, this is a unit that we are comfortable with. So I can find M dot right now using the number that I got. M dot will be 0.04053 kilograms per second. Okay, so we have the M dot, we have H2 and H1. We can plug everything back into this equation and find work. So let's do it. Okay, so I just cleaned up the calculation area. Now we can plug everything into the green equation and get that W dot is 0.04053 times 278.27 minus 259.3, which gives us W dot is 0.07688 kilowatts. So I found W dot. I already know Q dot L from before. I can calculate COP. So the COP of this refrigeration cycle is Q dot L over W dot. Okay, so Q dot L from before is 5.07 over W dot, which is 0.7688. That gives us 6.58. Okay, so let's move on to part B. Now in part B, we are asked to find the maximum coefficient of performance. The maximum coefficient of performance is only achieved when the cycle is reversible and ideal. In other words, it's operating on a Carnot cycle. So COP max, which is the COP of a Carnot cycle, is for a refrigerator 1 over T of H over T of L minus 1. T of H is the temperature of the outside air, 34 degrees Celsius, and the T of L is the temperature of the cooled room, 26 degrees Celsius. We need to convert them to kelvins. That will be 306 over 298 minus 1. This gives us 37.4. So the maximum COP achieved by an ideal cycle operating between the temperatures of 26 and 34 degrees Celsius is 37.4. Now, part C asks the minimum volumetric flow rate of the refrigerant at the compressor entrance if the compressor inlet and exit conditions were the same. Now, if the states of the working fluid at the entrance and the exit of the compressor is not changing, then by reducing the volumetric flow rate of the refrigerant at the entrance of the compressor, we are reducing the amount of work input of this compressor. Now, the minimum work input of a compressor for a cycle that is operating between these two temperatures can be achieved using the Carnot analysis. So, we are looking for the minimum work. M dot minimum at the entrance times the change of enthalpy is equal to the minimum work of the compressor. We can find the minimum work of the compressor using the maximum COP that we found in the previous page. So COP of our Carnot cycle is Q dot L over W dot minimum, right? Now, COP maximum that we found was 37.4. Q dot L, that is not changing, so that is 5.07 over W dot minimum. Playing with this equation, you get that W dot minimum is 0.1353 kilowatts. This is the absolute minimum power input that this cycle can work with. Now I'm going to plug this number here and find M dot minimum. Keep in mind that because the inlet and exit conditions of the compressor is not changing, H1 and H2 is not changing. We already know them. So we can just plug them from previous pages and find our minimum mass flow rate. So let's do it. So my minimum mass flow rate is minimum work 0.1353 over H2 minus H1, which is 278.27 minus 259.3. Do the math, we get that the minimum mass flow rate is 0.007132 kilograms per second. But this is not what the problem wants. The problem wants the minimum volumetric flow rate. So volumetric flow rate is mass flow rate times the specific volume at state 1. Again, the specific volume of state 1 has not changed, so we can use our previous number. We get 0.007132 times 0.007132 2.041118, which is 2.93 times 10 minus 4 meters cubed per second. Now, this is the final answer, but because the initial volumetric flow rate was given in liters per minute, let's change the units to liters per minute. You will get minimum volumetric flow rate at the entrance of the compressor is 17.58 liters per minute. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again and see you in another video.